In standard clinical neurofeedback, a patient presents with a specific symptom, like poor attention or elevated anxiety, and the practitioner attempts to map that symptom directly to a localized region of the brain. The common response is to apply a standardized, rote protocol designed to treat the electrical activity isolated in that specific area. This approach views the brain as a collection of independent parts, much like a mechanical engine, where a single component can be fixed without affecting the entire system. However, applying these rigid, localized protocols often fails to produce consistent, long-term clinical outcomes. The brain does not operate in localized vacuums, and it often resists attempts at isolated manipulation. Symptom-specific protocols are insufficient on their own because they do not account for how the brain actually functions as a whole. While we use a standard 10-20 EEG layout to record data, the brain actually operates through dynamic, interacting neural networks. Clinical efficacy depends on understanding how these networks communicate. Self-regulation isn't a localized switch. It emerges from the successful interaction of these pathways. The BCIA blueprint provides the structural methodology required to understand this systems-level physiology. This framework is an international reference point that defines how neurofeedback should be applied responsibly across different disciplines. For the practitioner, this requires a transition from merely recording electrical signals to understanding why certain physiological patterns emerge. Moving from symptom management to systems-level comprehension is the path to achieving international-level professionalism. Advanced practice begins with separating meaningful EEG signals from the background noise of standard artifacts. Even a clean signal is not an absolute indicator of a specific condition. If you take the exact same frequency band and place it into two different architectural network models, its significance changes. The physiological meaning of an EEG pattern is dictated by its network context. This contextual reality is why rote protocol memorization is an ineffective way to approach complex cases. By reading signals in context, practitioners can more accurately link underlying physiology to a patient's observable behavior. Treating a signal without first mapping its origin within the network is a significant clinical risk. Raw signals are clinically meaningless without context because it is the context that defines the behavioral outcome. The idea that specific cognitive tasks are limited to isolated hotspots in the brain is an outdated concept. In reality, any task involves multiple regions of the brain activating simultaneously and communicating across a distributed web. Within this interconnected system, neurofeedback acts as a reinforcement tool for the communication between nodes. The goal is not to force the brain into a specific, arbitrary range. Instead, neurotherapy facilitates the brain's own ability to develop optimal self-regulation across its networks. Targeted feedback strengthens the functional bridges between distant cortical regions. Advanced neurotherapy doesn't fix a broken part. It optimizes the systemic communication required for the brain to regulate itself. Practitioners often feel anxious when they see variability in a patient's EEG data from one session to the next. However, a linear progression model is biologically unrealistic for the brain's learning process. No two brains respond to stimuli in the exact same way, and responses will fluctuate. This variability is actually a valuable dataset, representing the brain's attempt to integrate new information. Rather than viewing these oscillations as a setback, practitioners should analyze them to see how the brain is adapting. Nonlinear progress is a natural reflection of neuroplasticity and internal recalibration. Tracking these microadjustments tunes the feedback loop to the patient's current state. Data variability is the physiological footprint of a brain learning to self-regulate, making linear benchmarks obsolete. There is a significant difference between memorizing isolated protocols and possessing a coherent understanding of brain physiology. In this workshop, Giuseppe Curenza teaches you to integrate separate pieces of data into a unified model of brain function. This systemic model changes how you view clinical data, building confidence from deep understanding rather than following rote instructions. This mindset aligns with the high standards set by the BCIA blueprint. This framework allows a practitioner to logically adapt their approach when they encounter clinical presentations they haven't seen before. Professional confidence is an emergent property of deep systemic understanding, not the byproduct of holding a certificate. The BCIA framework is recognized internationally because it provides a shared language for practitioners across different disciplines and countries. This shared language sets clear expectations for foundational knowledge and responsible application. Mastery of this framework also involves defining the ethical boundaries of the practice. This includes being clear about the limits of the method and what neurofeedback can and cannot achieve. Communicating with clients based on what is scientifically known ensures a higher level of professional integrity. Because this material is complex, the workshop sessions are recorded to allow for the repeated exposure and integration required for real mastery. Understanding the brain as a system is the sustainable path to international-level professionalism and the development of long-term clinical credibility.